So yeah, so we talked about address space randomization and its two flavors: the absolute address randomization or base address randomization, and relative address randomization. So the other second technique we talked about is randomizing the representation of data. Okay? So one thing you can do is that for each variable you can allocate a random mask. Okay? And what you're going to do is that you're going to take the conventional value of that conventional bit representation of that value, and you're going to XOR it with a random mask. Okay, so each variable has its own mask. So that means each variable's bit level representation in memory is going to be different. So each time you write that variable, you're going to do this XOR and then write. Whenever you read that variable, then you're going to again XOR it with the same mask. So because of the properties of XOR, so what ends up happening is that if you read and write in a legitimate way, then X and A will be the same. Therefore, these two masks will cancel out, and you'll end up with the original value B. But if there is like a buffer overflow, and so what you're doing is that you're using, you're writing to A, but you overflow past the end of A, and then you end up writing X. Then what's going to happen is that the value that's written is going to be written with A's mask, and so when you read X, then the value that's going to get read is this quantity. And since the mask of X and mask of A are completely different, you're going to get some random junk, right? So which means that if the attacker did an overwrite from A to X, then they would have succeeded in writing some random bits, right? And therefore they won't know what exactly happened. So that's what it does, and as a result, what this means is that even if you think about attacks that only target data, right? So for instance, I gave you this example of has the user successfully authenticated themselves by providing a password. There was this Boolean variable, right? If the attacker finds an attack that just corrupts a variable, right? Even that kind of an attack, which doesn't involve any pointers, can still potentially fail. Can fail here because of the masks not matching. Right? Because any kind of overflow, even of the simplest data types, can potentially be stopped. So there are many benefits, but there are also problems, and so I'm not going to talk about the problems in much detail, but the main issue is that sometimes you have what is called aliasing, which means that two variables point to the same object, and when that happens, it is obviously legitimate to use one of those variable names to write and read using the other variable name. And if you end up assigning different masks to these two variable names, then you will get junk, right? The program will break. So you need to make sure that if any two variables that can be legitimately aliased, they should somehow have the same mask assigned to them. And this, is an extra level of carefulness that's needed, and it's not always easy to get it right in really complicated C programs. Okay. And so it's something that remains sort of an interesting technique, but not very easy to apply. Okay, so summarizing what we have been discussing, so we talked about how to disrupt the takeover step, and the takeover step we said can be disrupted using randomization or augmented diversity, and so once again, the way diversity has been applied is that you randomize whatever the language, programming language leaves unspecified. Okay? And then by doing that, you can diffuse a wide range of attacks. So you should qualitatively distinguish between, techniques like stack canaries, which are very pointed, right? They are trying to protect against a very specific type of attack, versus techniques like randomization, which are very broad in scope, right? And they stop a wide range of attacks. Okay. So obviously, one would like techniques that are broad in scope and can stop a wide range of attacks, but it's difficult to find those techniques. Right? So there is randomization and there is randomization. Right? There isn't anything else that really has that kind of a broad ability to protect against this class of attacks. So before I close this discussion of memory corruption exploits, let me just say something about what is the current state of affairs, given all of the defenses that have been deployed. So, as I said before, operating systems and compilers have implemented things like Propolis, address space layout randomization, data execution prevention, and so on. Right? So the attackers now have to, work against all of these techniques. Right? And of course, attackers are always resourceful, and so they have often found a way to get around various around these defenses. So, for instance, address space randomization makes it difficult to figure out, where is the code that you want. Okay, so to deal with that, attackers came up with a technique called heap spray. So the idea is that, I don't know where, I'm going to write some data into this process memory, right? I'm going to inject some data into this process memory. I don't know where it is going to end up, right? So the way I'm going to overcome that is by injecting lots and lots and lots of data into the process memory, right? So my attack code is everywhere, right, in the process memory. Now, if I pick a random location to jump to, you'll still have my attack code, and therefore the attack will succeed. Okay. So this is the idea behind heap spray. In this particular form, heap spray here is still requires data to be executable. Okay. So this is often not such a big issue even these days, because when you think about the type of programs that they target, they are targeting typically things like web browsers, right? So these browsers run JavaScript, and JavaScript does something called just-in-time code generation, and just-in-time code generation requires that the code that they generate, that the JIT compiler generates, that must be executable. And for this reason, a lot of the if the attacker can somehow essentially control the JIT code that's generated, then they can do a heap spray even if there is a data execution prevention there, because if they just send a lot and lots of JavaScript code and that gets translated, and then it gets put into this executable memory location, and they can fill up a lot of the memory with this executable stuff, then heap spray can work even if BEP is enabled. So again, if I ask you to implement this, of course, you won't be able to implement it. That's not the idea. The idea here is to sort of just have a high-level understanding that whenever we design any kind of defense, attackers are often resourceful enough to find a way around the defenses. So another technique that's become somewhat common is what is called just-in-time ROP. So again, because of address-space randomization, partly, and also partly because these days software is updated at a very high frequency, right? So your Chrome may be getting updated every day or something like that. As a result, attackers don't know exactly what version of Chrome you are running and where are the gadgets, right? So it becomes, even if there is no address space randomization, it's difficult for them to figure out where are the gadgets that they want. So attackers came out with this interesting idea that if there is a information leakage bug that I can trigger from JavaScript. Okay. Now, why JavaScript? Because JavaScript can generally be attacker's code, right? So if you go to some website that is under attacker's control, then that website is going to send you a web page. In that web page, there can be JavaScript code. So essentially, attacker has the ability to, even before any exploit is effected, you are executing attacker's code, right? The only difference is that you are executing JavaScript code, which is a safe language, and therefore it doesn't give the attacker a whole lot. Okay, the browser environment is such that just executing attacker's code in the context of attacker's website doesn't give the attacker a whole lot. However, if the attacker, if the JavaScript can somehow trigger an underlying memory corruption bug or memory error, and this memory error allows the attacker to read some memory locations, then they can use this vulnerability to essentially read all of the program's code. Right? So they can read all the program's code, then they can figure out where are the gadgets that they want, and then they can put together a ROP chain and finish their attack. Right? So this is called just-in-time ROP because the attacker is, collecting the gadgets, at runtime. Right? So just before they are about to carry out an attack, they identify the gadgets that they want to use, and that is also becoming somewhat, more common these days. So very quickly, I will talk about the second approach. Right? So I said at a very